Okay, we have talked about measurement of impedance using the standing wave pattern. Today we will look at an example. In this example, we have an unknown load connected to a slotted air line. The SWR is given as 2, and it is recorded by a standing wave indicator, and minima are found at 11 cm, 19 cm, and so on the scale. When the load is replaced by a short circuit, the minima are 16 cm, 24 cm, and so on. If the characteristic impedance Z0 is equal to 50 ohm, calculate the wavelength lambda, frequency f, and the load impedance ZL. First, we are given the standing wave pattern. We are told that the minima occur at 11 cm and 19 cm, and so on. Okay, that is the case when the transmission line is terminated by the unknown load. You notice that the distance between the two subsequent minima, one is at 11 cm, another one is at 19 cm. That means that the distance between the two minima is 8 cm. The same is seen in the case when the transmission line is terminated by a short circuit. We see that the minima occur at 16 cm and 24 cm. So the difference between the two is also 8 cm. The distance between subsequent minima is equal to half wavelength. So if half wavelength is 8 cm, that means the wavelength lambda is 8 times 2. Okay, yeah, that means lambda is 16 cm. All right, and to find the frequency f, right, we need to know the propagation velocity. Propagation velocity v is equal to f lambda, f times lambda, right? So if we know the wavelength lambda and if we know the propagation velocity v, we can find the frequency f. So in this case, what is the propagation velocity? We are given that the transmission line is a air line. What it means is that the dielectric between the two wires is air. So in this case, we can assume the dielectric constant is 1, and so the propagation velocity is equal to the speed of light in vacuum, that is 3 times 10 to the power 8 meter per second. So therefore, from a wavelength of 16 cm, the frequency is propagation velocity divided by wavelength, and the propagation velocity is assumed to be 3 to 10 to the power 8 meter per second. That gives us a frequency of 1.875 gigahertz. Next, we want to find the impedance ZL. So to find this impedance, we need to know the SWR, and also we need to know the distance between the minima when the transmission line is terminated by a matched by the unknown load compared to the case the minima when the transmission line is terminated by short circuit. This is how it looks like, assuming this is the standing wave pattern when the transmission line is terminated by unknown load. The minima occur at 11 cm, 19 cm, and so on. All right, and then now if the load is replaced by a short circuit, we will have a minima occur at the load point itself. Okay, that means at the end of the transmission line we have a minima, and this minima will repeat every half wavelength. Every half wavelength in such a way that the minima occur as 16 cm, for 24 cm, 32 cm, and so on. All right. Since we do not know where is the location of the transmission line end, we can compare the minima when the transmission line is terminated by unknown load, compared to the case when the transmission line is terminated by a short circuit. So in this case we see the distance between these two minima is 16 minus 11, that's 5 cm, 5 cm. Okay, we can use a Smith chart, right? A Smith chart is a plane of reflection coefficient, where the real axis represent the real part of the reflection coefficient, and the vertical axis represent the imaginary part of the reflection coefficient. All right. Given the standing wave ratio, SWR is 2, right? That means when we draw the constant mismatch circle, the circle will cross the horizontal axis at the point where impedance, or the normalized impedance is equals to 2, right? So starting from this point, from the Smith chart, we can find the point where R is equals to 2, right? We can draw a constant mismatch circle. Okay, and then from the features of the Smith chart, we know that the impedance will change along this constant mismatch circle as we move away from the load. We will find the point of minimum voltage, and then 1/4 wavelength away we will find the point of maximum voltage at this point, and then another quarter wavelength, we will find the point of minimum voltage, and so on. All right, so that means this point which represent the location of minimum voltage, correspond to this point, and also this point. All right. So if the impedance at this point is given by this value on the Smith chart, all right. So what is the impedance at this point? That is 5 cm, 5 cm towards load, 5 cm towards load. The impedance at this point is equal to the impedance at this point, alright, which is also the location when the standing wave pattern is minimal for the case of short circuit. So the impedance at this point is the same as the impedance at this point. All right. Yeah. So that is a distance, yeah, of 5 cm towards load from the minimum point. Okay. So if this point represents V mean, yeah, the location of minimum voltage, we need to move 5 cm. Yeah, we need to move 5 cm towards load. Yeah, towards load means we move counterclockwise, yeah, on this constant mismatch circle. All right. Yeah. So what is 5 cm compared to the wavelength? All right. So 24 minus 19 is 5 cm. Yeah. And earlier we found that the wavelength is 16 cm. So that 5 cm corresponds to 5 over 16, yeah, which is 0.3125 lambda. Yeah. So 0.3125 lambda corresponds to 225 degrees. Yeah, that is the angle. If we use the formula 2 beta z, yeah, 2 beta z, yeah, that will give us 225 degrees. Okay, and so what it means is that on the Smith chart, starting from the location of minimum voltage, we need to turn 225 degrees counterclockwise. Yeah, so from this point, 225 degree counterclockwise, then we will end at this point, yeah, which is 45 degrees. All right, yeah. The intersection between this radial line with the constant mismatch circle will tell us the impedance, yeah, at this location. The impedance at this location, yeah, which is equal to the impedance at this location. All right, and from this magnitude and this angle, we get the magnitude and phase of the reflection coefficient. And to read the impedance at this point, yeah, we can refer to the Smith chart. Yeah, that is the circle of constant resistance. Yeah, and the circle of constant reactance. Yeah, that cross this point. All right. Yeah, then we can read the impedance. Yeah. So in this case, we get a normalized impedance of 1.4 plus j 0.75. That means, yeah, if we use the Smith chart, we find that the constant resistance circle that pass through this point, yeah, the constant resistance circle that pass through this point is 1.4. All right. Yeah, and the constant reactance circle or curve, yeah, that pass through this point, yeah, a curve that is like this. All right. Yeah, you can read the value at the circumference of the Smith chart. Yeah, you'll find that that value, yeah, that value is 0.75. Yeah, so that gives us a normalized impedance of 1.4 plus j 0.75. That's the normalized impedance of the unknown load, right? But what about the absolute impedance? Yeah, this is the normalized impedance, right? Yeah, the absolute impedance is the normalized impedance multiplied with the characteristic impedance, yeah, which is 50 ohm in this example. So that gives us impedance of 70 ohm plus j 37.5 ohm, right? Yeah, so this is the impedance of the unknown load at this location, which is also equal to the impedance at this location, the location at the end of the transmission line where the unknown load is connected there to the transmission line. Okay.